Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in this course Advanced Thermodynamics and Combustions, that is module 2, Entropy and Exergy. So, in this lecture we will cover the entropy analysis part 4, and in prior to this class we have exhaustively discussed about second law analysis and its consequence or statement in terms of entropy. This particular lecture will focus mainly on isentropic process, isentropic efficiency and polytropic processes. Just to emphasize the fact that at the UG level, you might be aware of the term isentropic efficiencies, which are normally applied for the steady flow devices. These steady flow devices includes compressors, turbines, nozzles, diffusers, pumps, and they are the basic components for a steam or gas turbine power systems. Now, with respect to this particular course, although this is a kind of a repetitions, but I will further emphasize the fact that entropy analysis plays a vital role, and in particular the term which we are going to discuss today, that is isentropic efficiency, is the benchmark for all practical devices. So, in fact, this particular lecture is mainly devoted to the applied part of this course. So, let me start. First is isentropic process. We have already discussed the term isentropic, which means entropy is a constant parameter when the system undergoes a change of state, and this isentropic word is very vital in the thermodynamic analysis of turbo machine components. In fact, it relates the thermodynamic parameters between two states. As you can see in the pressure, volume diagram or temperature entropy diagrams, one can draw various thermodynamic processes involving a constant pressure process, constant volume process, constant temperature process or isothermal process, or it can be any processes that bears the name polytropic. And in fact, all these processes are quasi-static in nature, which means we can use these thermodynamic equations as a reversible internal reversible process. So, we have to analyze all these thermodynamic parameters for an isentropic process. The ideal choice that we should look is the temperature entropy or enthalpy entropy diagram. That is because constant entropy line is represented as a vertical line. Now, when the process is analyzed for estimation of different parameters, we look for the thermodynamic property tables which are available in all fundamental thermodynamics books. we also will explore Mollier diagrams, which is nothing but the enthalpy entropy diagrams. And in fact, for ideal gases, we have derived the isentropic relations between two states, that is pressure, temperature, volume, specific volume and density. So, this relation is very vital for analysis of isentropic process. Now, let us move back to the importance of this isentropic process and when we deal with isentropic efficiency. In fact, all the steady flow devices that are used in the power plants, they undergo certain thermodynamic processes, and the analysis of these processes is dealt with one particular parameter, that is, if the process is internally reversible and for which the analysis can be done through isentropic process. So, in a sense that the isentropic process is the benchmark for the idealized performance of the component. So, if I can summarize this fact, the steady flow devices includes components like turbines, nozzles, compressors and pumps. These components are modeled for two situations. One is the conservation of energy by using the first law of thermodynamics. Also, we use mass balance equations, and most importantly, it is also under consideration, that is entropy, which is used for steady state control volume. So, basically analysis involve mass and mass balance, energy balance and entropy balance for a control volume. Now, when you deal with the entropy balance, we normally use the time averaged values of the either entropy, mass or energy. Now, because of the nature of the different components, for example, turbine is meant for producing work, nozzle is meant for enhancing the velocity, compressors are used for raising the pressures, in fact pumps are also used to rise in the pressure for liquids. So, because of this nature of the requirement, the terms that is associated in the energy balance, one which is heat transfer term through the control volume or the work transfer term for the control volume, that can be set to 0 or a negligible number as compared to other parameters. So, when the QCV, that is heat transfer term, can be set to 0, because if it is small relative to energy transfers across other energy transfers across the system boundary. Now, work transfer term drops to 0 when there is no rotating shaft or physical displacement of boundary. In such cases, we can neglect this term. In some instances like turbines and compressors, the kinetic and potential energies are negligible. So, for all this component analysis, if we neglect this term, and then we can define a term which is called isentropic efficiency, which is considered as the idealized performance indicators with respect to actual performance of the component. All these components use steady flow equations, and the analysis is done through a control volume, and when I say control volume, there is a possibilities of mass transfer as well as the energy transfer. So, for a control volume at steady state, in which the flow is both isothermal at constant temperature as well as internally reversible, appropriate entropy balance equations can be written. Obviously, we also know the work or heat transfer per unit mass through a one inlet one exit control volume. That means, energy balance equations can be written. So, in our last class we derived the relations for the internal reversible process, that is entropy change. We also dealt with the heat transfer term for an internal reversible process, work transfer term, and ultimately we end up in having the expressions for heat transfer and work transfer in a control volume analysis in a simplified term, like heat transfer is nothing but the integral of TdS, work transfer through the control volume per unit mass is integral of BdP. Basically, it means that on a TS diagram, when the process undergoes a change of state, the area under this curve represents the heat transfer. Similarly, in a PV diagram for an internal reversible process, when the system undergoes a change of state, and this area represents the term VdP. So, this is the practical significance of work transfer term and heat transfer term for internal reversible processes. In fact, these two equations will be heavily used in the analysis of steady flow components. So, let me start the first important component for which we are going to calculate the isentropic efficiency, and the component is turbines. So, we all know the turbine produces power. So, it is a device which is designed to produce power as a result of gas or liquid passing through a set of blades which is attached to shaft, and the shaft is free to rotate. Now, with the selection of control volume enclosing a steam or gas turbines, net kinetic energy of the matter flowing across the boundary is small, which can be neglected. So, I told the turbine is designed for producing the power. So, the change in the velocities associated with the system is normally neglected, because these are very small numbers as compared to other parameters. So, typically the turbine processes is represented by simplified diagram like this, in which we get work Cv by m dot. So, the control volume is chosen in such a way that the gas that enters to the turbine from the state 1 expands to its full capacity, and when the gas it leaves, that is at state 2, it is fully expanded, and whatever work is developed through this process, it rotates this shaft. So, the system undergoes a change of state from 1 to 2, and this turbine process we can represent in a temperature entropy diagram. So, this is an expansion process. So, initial state your P1 is higher and final state P2 is lower. So, in a TH diagram we can draw two constant pressure lines. The first point is P1 and second pressure line is P2. So, the state is located at point 1. When it expands isentropically, it goes to state 2s. So, you can remember that this is an isentropic process and is a vertical line, but if there are internal irreversibility, then the actual process will land at point 2, but at a higher temperature. So, in other words, we can say that gas in a non-isentropic process has not expanded fully. So, there arises the term isentropic efficiency of the turbine. So, from these expressions we can find out the actual work. So, actual work is H1 minus H2. So, in fact, this H1 minus H2 term comes from the steady flow equations, and when you do the entropy balance for the control volume, we can write S2 minus S1 is greater than or equal to 0. Now, if it is greater than 0, that means there is a irreversibility associated in the expansion process. If it is equal to 0, that means there is no irreversibilities in this process. So, from this, when S2 minus S1 is equal to 0, we get the reversible work, and which is considered as the maximum work. So, H1 minus H2S. So, thereby we represent the isentropic efficiency as the ratio of H1 minus H2 divided by H1 minus H2S. So, H2S is your isentropic enthalpy when the gas is at state 2. So, here let us talk something else, that the isentropic efficiency is expressed in terms of enthalpy, and when you use the steam, so normally the expression is a general term. When you talk about steam turbine, we refer the diagram what we call as a Mollier diagrams. So, the snapshot for this Mollier diagram which you can represent. So, these are the constant pressure lines. We can write one is at P1, other is at P2. So, depending on the initial state conditions, I can represent this process, the state as 1. Now, had this process been isentropic, then I would have come to 2S. If since this process is not isentropic, I land up in H2. So, here we can directly get the values of enthalpies from this Mollier diagram. So, you can say for this value is H1 and this value will be H2S, and this number will be H2. So, H1 minus H2 is the denominator term, and H1 minus H2 is the numerator term, and H1 minus H2S is the denominator term. Now, if we use the gas turbine, that means the H can be represented as Cp times T. For a gas equations, you can write Hcp times T. Now, if you use that, so instead of in Mollier diagrams, we can directly use the temperature entropy diagrams as I have explained. Okay. Now, another analogous term to expansion is nozzle. Nozzles. So, what does this mean is that, so normally the nozzles are used to generate higher velocity. So, that means schematically they are represented as that of turbine, but their main intention is initial state is defined in terms of pressure P1 and I can say velocity or U1, and final state is decided by pressure P2 and velocity u2. So, when the nozzle action is performed, your u2 is greater than u1 and P2 will be less than P1. So, this nozzle action is due to expansion of fluid from its initial state to final state, and this nozzle can be a steam nozzle or it can be used for analysis of air. So, that means working fluid could be a steam or air. Now, when you say it is a steam nozzle, we use again this Mollier diagrams, and here we can see in a similar sense we can okay. So, now before you go further, we can find out these energy balance equations, which is H1 plus V1 square by 2 minus H2 plus V2 square by 2, all is equal to 0, that is so in this control volume we can simply write W dot CV is equal to 0 and Q dot CV is equal to 0. There is no work transfer or no heat transfer. So, using this equation we are getting this. Now, the isentropic term is defined that if the gas has not expanded to its full capacity for generating the velocity, then it would be then it will land off in having a velocity V2 square, sorry, in this case we can write U2 square or by 2 for an actual process, U2 square by 2 for the isentropic process. So, how do you find out? So, initial state we can represent this in the Mollier diagrams. We can say the gas expands from this pressure P1 and to P2. So, from this initial state we can write, if this process is isentropic, then it will land up in reaching the point 2s. If it is a non isentropic, it will land up in point 2. So, this particular term or scale will be V2 square by 2, and this particular term will represent V2 square by 2 if the process is isentropic. So, based on this we define the term isentropic efficiency. So, the isentropic efficiency of the nozzle is defined as the ratio of actual specific kinetic energy of the gas leaving to the nozzle to the kinetic energy at the exit that would be achieved in an isentropic expansion. Now, I have also given another term diffuser. So, it is a just an opposite process that a nozzle does. So, similar figure for a diffuser can be, sorry, I have made a mistake. So, it should be the other shape. So, this is the diagram for a steam nozzle where initial area is larger than the final area. For a diffuser, the final area is larger than the initial area. So, we say it is a initial state is P1, velocity is U1, final state is P2, velocity is U2. So, the other action would be, so here U2 is less than U1 and P2 is greater than P1. So, this analysis also we can do through control volume, and we call this as a diffuser action. Now, we will move to compressors and pumps. The word compressor is used in the steady flow devices which takes work as a input, that means work is done on the system, and as a by virtue of its the pressure of the fluid increases. So, and if we are using the air or gas as a working fluid, the term compressor is mostly preferred. If your working fluid is water or any liquid, the term is pump is fits as a most appropriate term. So, in whether it is a compressor or pump, the work transfer is always negative because it requires the power input. For same pressure rise, we can see that for a same pressure rise, a pump requires smaller work per unit mass flowing through the compressors, because specific of the volume of liquid is smaller compared to the vapor. So, because of this reason, when you deal with the steam power plant, pump work is assumed to be smaller or very small as compared to turbine work. Now, when you deal with the gas turbine plants, the compressor work and the turbine work, they are at par. It cannot be neglected. So, that sense we say that turbine always drives the compressor. So, analysis is almost in a same as you did it for the turbines, but very basic difference that we have here, the isentropic work, which is the maximum work, will be less. If the process is isentropic, the pump will consume less work. If the process is internally, if there is internal irreversibility is present, then pump work will be higher. So, when you define the isentropic efficiency for the compressors, the numerator term represents the isentropic work and the denominator term represents the actual work. Now, the last segment of this is a polytropic process. So, basically we have given a equation of state for a polytropic process as Pb to the power n is equal to constant. Ideally, the word polytropic process is assigned when the system undergoes quasi equilibrium change of states, and the equation of state can be written as Pv to the power n is equal to constant, and these equations can be applied for any gas, but if it is an ideal gas, this Pb becomes RT. So, in our analysis, why we are dealing with this thing is that here the n quantifies the nature of the process. So, in a PV diagram, the process that can happen is we can represent as Pv to the power n is equal to constant. Process goes from 1 to 2. This nature of the process depends on what value of n. So, there are possibilities that n can be 1, which is isothermal, n is equal to gamma, which is adiabatic, or sometimes if it is reversible we say isentropic, and for any value of n we if n is any value between 1 to gamma if you put as 1.4 for air. So, it between 1 to 1.4, so it becomes a polytropic equation. Typically realistic number of n is about 1.3, which is normally used for reciprocating compressor. So, why I am saying this is, so reciprocating compressor is another area of application, although it is not a steady flow device, because there are it is a cyclic device. But anyway, our main intention is to quantify the work transfer for two situations. One is in fact, it is an internal reversible work which is represented as a integral of V dP. Now, when n is not equal to 1, it is represented in this form, that is n by n minus 1 P 1 B 1 minus P 2 B 2. Now, if n is equal to 1, the equation gets modified as work transfer equation becomes P 1 V 1 ln P 2 by P 1. Now, here you impose the ideal gas state equations, which is P V is equal to R T. So, when you use this takes the term of writing the equation of states what happens to the temperatures. So, you can have equation like T 2 by T 1 is equal to P 2 by P 1 to the power n minus 1 by n. Now, based on these things, your the work transfer equations further modified in this form. So, basically we are replacing the volume in terms of temperature, specific volume in terms of temperature. Now, we are going to discuss some of the numerical problems. So, the first problem is based on a turbine which operates at steady state and it develops 75 kilojoule of work, and this turbine is used in a, maybe you can say it is a gas turbine power plant system, in which air enters at 3 bar and 400 degree Kelvin and leaves at 1 bar. So, basically your working fluid is air. To start with, first thing what you have to do, you have to do the schematic diagram. So, for schematic diagram we can represent the nature of a turbine process. The gas expands. So, the state 1 is pressure P 1 is 3 bar, and T 1 is 400 Kelvin, and final state your P 2 is 1 bar, T 2 is not known, but what it says is we can assume this is a control volume. That means, if this control volume analysis, if it does, if you do it, what it says is that work output it produces 75 kilojoule per kg. So, we can assume that this is your actual work. So, we can say W dot C V by m dot is equal to 75 kilojoule per kg, and what we do not know is W dot C V by m dot for an isentropic process, because the turbine process is isentropic, if you can assume. So, in your TH diagram the process can be written as expansion of gas from state 1 to 2S isentropic process, it is 2. So, this for this we can write it is nothing but Cp times, or we can write this simply as H1 minus H2S, or Cp times T1 minus T2S. So, what we know, P1 T1 you know, P2 and T2S we do not know. So, to do that we can recall this isentropic relation. that says that T2s by T1 is equal to P2 by P1 to the power k minus 1 by k. K is your specific heat ratio, that is 1.4, and also you can find no Cp is 1.005 kilojoule per kg Kelvin. Okay. So, from this we know all the parameters. So, T2s can be computed as it is T1 is 400, P2 by P1 is 1 by 3 to the power k minus 1, that is 0.4 by 1.4. So, this becomes, the value would be 292.5 Kelvin. So, we know T2s, then we can find out what is W dot Cv by m dot for an isentropic process, that is 1.005. T1 is 400 minus 292.5. So, this number would be about 108 kilojoule per kg. So, we have two ratios, one is W dot Cv by m dot, which is for actual process, other is for isentropic process. Then by definition of isentropic efficiency for turbine, W dot Cv by m dot, here actual work should be numerator, isentropic work should be in the denominator. So, turbine efficiency becomes 75 by 108. So, this number is about 70%. Okay. So, this is how you can find the efficiency, isentropic efficiency for the turbine. The next problem is talk about steam nozzles. So, normally steam nozzles operate from is used to generate thrust. So, schematically the steam nozzle's shape is defined in this manner. It is a basically convergent divergent nozzle, and the control volume can be represented in this manner. So, your initial state is 1, final state is 2. So, your main intention is V1, that is, or U1 is your initial velocity, which needs to be increased to U2. So, in this problem the initial velocity is given as 30 meter per second, and this is not known, final velocity is not known. Pressure condition is 10 bar, temperature is 320 degree centigrade, and exit pressure P2 is given as 3 bar, T2 is 180 degree centigrade. So, it is a steam nozzle, remember it is a steam nozzle, which means we need to use steam table to evaluate enthalpy. So, for the initial state 1, so for the based on the condition P1 and T1, 10 bar and 320 degree centigrades, we can find out H1 as 3093.9 kilojoule per kg, and state 2 at state 2, that is based on the condition P2 and T2, 3 bar and 180 degree centigrades, we can say your H2 is 23.9. Now let us see, since nothing is given to us, only from pressure and temperature diagram we are getting this data. So let us talk about the molecular diagram representation, where the gas from its initial states expands to the final state, that means initial state, and if the process is isentropic, it reaches at 2s. If the process is non-isentropic, its process reaches at 2. But what the data was given, condition 1 and 2, and obviously they must represent the actual state. Now to find this what happens to this isentropic process, if this gas or steam would have expanded in an isentropic manner, it would have raised to H2S. Now on this line, on this line 1 to S process, your entropy remains constant. So I can say S1 is equal to S2S. Now for this P1 and T1, I can find S2S as 7.1962 kilojoule per kg Kelvin, and for this value we can find H2S. H2S would be 2813.3 kilojoule per kg Kelvin. So this number we get from the data of state 1. This number we get from the data state 2. So now we are in a situation that we can write the energy balance equation which says H1 plus U1 square by 2 is equal to H2 plus U2 square by 2. So this means U2 square by 2 is equal to H1 minus H2 plus U1 square by 2. By putting this number, we can say U2 square by 2 is equal to 3093.9 minus 2823.9 plus 30 square by 2. So this term is 270.5 kilojoule per kg. Then we need to find out U2s square by 2. So again we can rewrite this equation as H1. You can rewrite this equation in the manner that U2 square by 2 for an isentropic process would be H1 minus H2S plus U1 square by 2. So here H2S is 2813.9. So 3093.9 minus 2813.3 plus 30 square by 2. So U2 square by 2 for isentropic process is 281 kilojoule per kg. So now we can find the isentropic efficiency for the nozzle, that is U2 square by 2 divided by U2 square by 2 if the process is isentropic. So by putting this number, we can get the isentropic efficiency is about 96%. Okay. Now we will move to third problem, which is based on a reciprocating compressor, and for this reciprocating compressors we are going to find out work and heat transfer per unit mass of air, and this is nothing but the for an internal reversible process. So, first thing we have to draw, since it is a compressor, so a PV diagram will be most appropriate. That is, we can say pressure volume diagram. The system goes from 1 to 2, and this equation is written as P v to the power 1.3 is equal to constant. So, basically this is nothing but your area under this diagram. Okay. Pressure is, this point 2 is 4 bar, initial pressure is 1 bar. So, we recall that okay. So, we have P1 1 bar, T1 20 degree centigrade or 293 Kelvin, P2 is 4 bar and your polytropic index is 1.3. So, we recall our attentions for these equations, that is we require also T2 which is not known. So, you can use this equation T2 by T1 for an ideal gas, that is with PV to the power 1.3 constants and PV is equal to RT. The T2 by T1 we can write as P2 by P1 to the power n minus 1 by n. So, all the number is given. So, this equation will give you T2 as 293 into 4 to the power 0.3 by 1.3, and this number would be 403 Kelvin. So, we know T2. Then let us find out what is W dot Cv by m dot. So, recall our previous equations, that is minus nr by n minus 1 into T2 minus T1. So, all the number is given. So, it is minus 1.3 into 0.287 divided by 1.3 minus 1, T2 is 403 minus T1 is 293. So, W dot Cv by m dot is equal to minus 136.8 kilojoule per kg. So, the negative sign indicates work input to the compressor. Now, in similar way we need to find out the heat transfer. So, we can recall our steady flow energy balance equations. Q dot Cv by m dot is equal to W dot Cv by m dot plus H2 minus H1, and here H2, since it is air, we can find out H2 minus H1 is equal to Cp times T2 minus T1. Okay. So, by putting this number we can find out that this is already find 136.8 plus H2 minus 1 would be 1.005 into T2 minus T1 403 minus 293. Again this number is, if you simplify this, Q dot Cv by m dot is minus 26.25 kilojoule per kg. So, this term negative means means heat is generated. So, and it is coming out. So, by virtue of this, the air temperature is increases. So, with this I conclude this lecture for today. Thank you for your attention.